Okay. This is second worst of them all. I left space so we could add worse ones afterwards. Nice. But a spotlight on the ground, the most fun part about these is drawing the picture prior to having to do the math. So if the math is really bad, at least you've taken the nice time to draw a nice picture. So spotlight on the ground. Let's go. Here's my spotlight. Oh, we'll get some shiny. Oh, this is nice.
You don't get that.
You might have to bring some pencil crayons to class moving forward. So there's our spotlight. It's on the ground. It shines on a wall 10 meters away. So here we have our wall, and this is 10 meters away. A man 2 meters tall walks from the spotlight towards the wall at a speed of 1.2 meters per second. What's that? Like this part, this is supposed to be a nice straight line. So you're already making fun of my drawing. I'm just a little bit hurt, and now I've got to recenter my smartboard. It was so bad that you thought I meant it on purpose. Okay.
Did you actually get still?
There we go.
You actually convicted of stealing? Then you gotta put the guy at
Here we go. Straight. Is that better?
No.
And this guy is moving in this direction at 1.2 meters per second. How fast is the shadow? So if we extend this line like this, right, here's the shadow of the guy. Ooh. How fast is that shadow decreasing when he is 3 meters from the wall? Wow, we've got a lot of things happening here. The key to this is recognizing that we have similar triangles. That the triangle made with the shadow and the light, the bigger triangle, is a similar triangle to the smaller triangle made with the light and the guy.
The guy starts on the spotlight.
The guy is somewhere between the spotlight and the wall. He's walking towards the wall at 1.2 meters per second. He's starting there, yeah, at the spotlight, walking towards the wall at 1.2 meters per second. So as he gets closer and closer to the wall, his shadow is decreasing.
So if he was to walk the entire distance, he walks 10 meters?
If he would walk the entire distance, he'd walk 10 meters. And we need to find out how fast the shadow on the wall is decreasing. So I'm going to call this y. Can you see that we are trying to find dy dt? We need to decide what is going to be x. And depending on what you choose as x will change the question. And there's more than one thing that you could decide to be x. Like you could make this x, or we could make this x. And it will make a difference because if I make this x, then my dx dt will be positive 1.2 meters per second because x would be increasing. If I make this x, then my dx dt would be negative 1.2 meters per second because my x would be decreasing. So which one do you want to try?
The inner one.
Let's stay positive because it's going to be a hard question. Okay. Dx dt then is 1.2 meters per second. And we're going to try and find out how fast y is decreasing.
X is the distance away
The distance away from
from
the light. So this question then becomes, what's dy dt when x equals 7? Okay? If we had the x in the other place, we would say, what's dx dt when x equals 3? Now, since these are similar triangles, that means that their ratios need to be the same. This man is 2 meters tall. Does it make sense that in the yellow triangle here, that the ratio of x divided by 2 has to be the same as the ratio between that length and y? So how do I set that up? So I'm going to use ratios here in a similar triangle. I'm going to say that x divided by 2, that ratio of that side to that side, has to be the same as 10 divided by y. Because I know that this distance on my purple triangle is always 10. So I can leave it like this and do my derivative with respect to time. I can multiply both sides out. That's saying x times y is equal to 20. I could do that as well. I can manipulate this equation however I would like to make it match up. If I do it, which one do you want to do the derivative of? You want to see that it works with both? Okay, let's say we start with this one because you don't want to mess around with your equation and you want to take the derivative with respect to time of this equation. On the left-hand side, that's just going to be a half dx dt. The right-hand side, that's going to be negative 10y to the negative 2. So in my head, I brought the y up to the top and I made it y to the negative 1. Did my exponent law, multiplied by dy dt. So based on what we have here, we have 1/2 dx dt, which we know to be 1.2, negative 10 over y squared dy dt. So in order to figure this out, we need to know what y is at that moment. So again, let's look at our triangle, and what we're trying to find is what's the value of y at this moment. Again, we can use ratios, right? We know that 7 over 2 has to be the same as 10 over y. So at this moment, when he's 3 meters away from the wall, at that moment, y will be 20 over 7. Plug that into our equation. So here we have 0.6, negative 10 over 20 over 7 squared dy dt. Is this some good mental math about to happen here?
I'm scared.
Negative 0.483, 489. Should we do some simplification here instead?
No, no.
With fractions? Without a calculator?
I convert it to that.
Sure. Convert it to a fraction just to...
Negative 24 over 4.
Negative 24 over 49? And we should include our units. It was meters per second. So in this case, we had to know some facts about similar triangles. And anytime you're going to be walking towards a spotlight shadow question, sometimes the spotlight's a lamppost and you're walking towards your shadow, we're going to get into these types of questions where you're going to have to analyze your similar triangles. So let's recap and look back at what we did. I'll view the whole thing on one page here. We drew a wonderful picture. Okay, we should take pride in that to start off with. And we chose where our x value would be. Now, based on where we chose our x value, in this case, our dx dt was going to be positive 1.2 meters per second. We used the idea of the similar triangle to set up our equation, because there's a relationship between x and y. And so in the smaller triangle, basically we're using our tan ratio, well, sort of our tan ratio. We did adjacent over the opposite side in both of them. But what you're really doing is using the idea of a tan ratio that's not going to change no matter how big or how small your triangle is. We could take the derivative with respect to time with that equation, and then we considered at what time do we want to figure out things, and what does y equal at that specific time. I find for students, sometimes the hardest part is you put your values in before you take the derivative of the equation as it changes. And then everything goes away because derivatives of values are 0. And then you're like, what did I do wrong? So you have to remember that we're setting up our equation as a relationship when things are changing. And you know that both x and y are changing here. And then we plug in our specific values once we've done that derivative to find what's happening at a specific point in time.
Got it.
Okay.